Okay, now let's go for the 3 cross 3 matrix. Now here there are some more possibilities. So the first possibility, if you have a 3 cross 3 matrix, if you get 3 different eigenvalues, then you find these corresponding eigenvectors, they have to be linearly independent. Why so? Again, by the theorem, eigenvectors corresponding to distinct eigenvalues are always linearly independent. So if you have a 3 cross 3 matrix and you get 3 different eigenvalues, then your job is done. You find those 3 eigenvectors corresponding to those eigenvalues, and therefore you will have c1y1 plus c2y2 plus c3y3 as your general solution. Okay, now that is the first case. I'm not taking that example. So even if you want some, I can give you one randomly. So if I take y prime is equal to 1 0 0 0 2 0 0 0 3. So this is a diagonal matrix. Eigenvalues are 1 2 3, the diagonal entries, and if you try to find the eigenvectors for 1 2 3, it will be 1 0 0 0 1 0 0 0 1. Okay, so respectively. So this will be the 3 eigenvectors, and the general solution will be c1y1 plus c2y2 plus c3y3. That was a bit fast, but I hope you understood what I want to say for this case. So this case is simple. Okay, let's go for the next scenario. Suppose if you have this as your system. Now if you try to find the eigenvalues, same thing, determinant of a minus lambda I equal to 0, and you get a cubic characteristic equation, and if you try to find the roots for that equation, the roots are coming out to be minus 3, minus 3, minus 6. Well, you can verify if you wish, but yeah, these are the eigenvalues. Now for you find the eigenvectors for lambda equal to minus 3. What you will do, you will solve a plus 3i into v bar equal to 0 bar. And if you try to solve this system, your v bar will come out to be, you will get this two as your linearly independent eigenvectors. 1 0 0 times v1 plus 0 2 1 times v3. You can do the calculation. If you find any mistake, you please correct me in the comment section, but I think these are correct. Okay, so this is what my v bar will be. So therefore, what are the eigenvector? 1 0 0 is my first eigenvector, and this is my another eigenvector. They are linearly independent. So therefore, what is the one set of solution? The one set of solution is nothing but 1 0 0 into e raised to minus 3t, and second solution is 0 2 1 into e raised to minus 3t, because we were getting two independent vectors. So this was my y1 and y2. Now for minus 6 also you find the eigenvector, and it will come out to be 2 by 3 1 minus 1. This will be the eigenvector, and therefore the third solution will be eigenvector into e raised to eigenvalue into t. Therefore you have 3 linearly independent solutions, and therefore your general solution will be c1y1 plus c2y2 plus c3y3. So here the eigenvalues were repeating, but then you were getting linearly independent eigenvectors. That means your am was equal to gm, your arithmetic multiplicity was equal to geometric multiplicity. So there was not an issue, you got 3 linearly independent solutions. That was the second case. But now suppose the eigenvalues are repeating, and again the same thing. What if you don't get enough eigenvectors? Okay, then again the generalized eigenvectors comes into picture. So let me take those example now. Okay, now take this as your example. So what is your y1 prime? It is y2. What is y2 prime? It is y3. What is y3 prime? y1 minus 3y2 plus 3y3. So that is your system, and if you write in the matrix form, this is what you have. You find the eigenvalues, determinant of a minus lambda I equal to 0, then 1 comma 1 comma 1 are the eigenvalues. You find the eigenvector, and in this case you get only one eigenvector, and that eigenvector is nothing but 1 1 1. You get v1 equal to v2, and you get v2 equal to v3. So therefore all the 3 components are same, and therefore your one solution is 1 1 1 e raised to t. Now you want 2 more solution, right? Because it's a 3 cross 3 system, so you should have 3 linearly independent solutions. Now question is, how will you find remaining 2? Again the same thing, the notion of generalized eigenvector will come into picture. Now what will be my y2? As I told you for 2 cross 2 case, the same thing. My y2 will be t times y1 plus u bar into e raised to t. What is my u bar? It is the generalized eigenvector, which can be obtained by solving a minus lambda I, lambda is 1, u bar equal to v bar. You won't take 0. If you want to find u bar, you will take equal to v bar. What is v bar? 1 1 1 you can take. Okay, to find u bar, you have to solve this system. Now do the same thing, you do the row operation. So if you do r3 plus r1, so what you will get? This is what you have. When I do r3 plus r1, 0 minus 2, 2. Do not forget to do the same operation on the right hand side as well. So 1 plus 1 is 2. Okay, now again if I do r3 minus 2 times r2, my third row will become 0. So what do I have? I have So this is what I get. Now if you try to solve this system, what do you have? Now if you try to find your u1, u2, u3, what do you get? From second equation you have u3 is 1 plus u2 and u1 is u2 minus 1. And therefore what your u bar is? Your u bar is nothing but what is u1? u2 minus 1, u2 as it is. What is your u3? 1 plus u2. And now you can rewrite this as u2 times 1 1 1 plus minus 1 0 1. Now again for simplicity you can take u2 equal to 0 because u2 is any number. So any combination of this will be your eigenvector. So let's take u2 equal to 0 for simplicity. You can take 1, you can 2, you can take 2, you can take pi, anything, but let's take 0. So your u bar will be minus 1 0 1. So once you have your u bar, you put it over here, you have second linearly independent solution. Now question is, how will you find third linearly independent solution? And the answer to that is, this is that answer. This is your y3. So what you do is, you do t square by 2 into y1 plus u bar t into e raised to lambda t. y1 we already have, u bar we got from here. Now you add one more term, which is nothing but w bar, which is again the generalized eigenvector. And how do you obtain w bar? You simply solve the equation a minus I into w bar is equal to, now u bar you take, because to find u bar you took v bar. Now to find w bar you will take u bar. So this is how you solve this. You solve this, and your homework, first homework for this lecture is, you have to tell me what is your w bar coming out to be. So that is the first thing you have to do. And once you have w bar, you plug in over here, that is your y3, and therefore your general solution will be c1 y1 plus c2 y2 plus c3 y3. So this is how you will deal if you have three same eigenvalues but only one eigenvector. So for one eigenvector, this is the first solution, and this is what your generalized solutions are, and you have then the general solution. Now someone can ask, what if I have 1 1 1 1, all I have eigenvalue 1 4 times, and I have only one eigenvector which is v bar? Then you can find y2 y3. Question is, what is y4, the fourth linearly independent solution? Well, I searched but I didn't got a solution, but what I think, if I try to generalize from here, my y4 will, in that case, here if you observe, it's simply integrated. So what I think is, my y4 has to be, if I integrate this, t cube by 6 into y1 plus, here it will be u bar t square by 2 e raised to lambda t plus w bar, you apply t e raised to lambda t plus at the end you take x bar e raised to lambda t. How will you find x bar? A minus lambda I into x bar equal to, now we will take w bar. Okay, so to find u bar, on the right hand side you will take v bar. To find w bar, on the right hand side you will take u bar, and for x bar on the right hand side you will take w bar, and then one can keep on going. So this was my another case. Now only one last case is remaining, so let me cover up and then we will stop. Okay, so for a 3 cross 3 matrix, either you have 3 distinct eigenvalues, great, you have 3 linearly independent eigenvectors. If suppose eigenvalues are same, suppose 1 1 1, and for that if you are getting 3 linearly independent eigenvectors, great, again you have c1 y1 plus c2 y2 plus c3 y3. But for the same eigenvalues, if you are not getting the same number of linearly independent eigenvectors, then you have to go for the generalized eigenvectors. And among them, the first case was, you have 3 same eigenvalues and only one eigenvector. Then this is what you do. Now the last case is remaining, when you have 3 same eigenvalues, and suppose if you are getting 2 linearly independent eigenvector, question is, how will you find the third generalized eigenvector? So let's take that case and then we will stop. So this is the system, suppose you have, it's a 3 cross 3 system, and you have the same eigenvalues, and you are getting 2 eigenvectors, u bar and v bar. Question is, how will you find your third linearly independent solution? So since for 2 independent eigenvectors, I have 2 solutions. Now what will be my third solution? So now the question is, what here you will choose, whether you will choose y1 or y2. Well, you don't choose y1 and y2, we don't do any discrimination. So what do we do is, we take y3 as tx e raised to lambda t plus w bar e raised to lambda t. Now what is w bar? It is the generalized eigenvector. So you solve a minus lambda I into w bar equal to, what you will take, whether you will take v bar or u bar. Okay, it's not sure which one to take. Usually you take linear combination of v bar and u bar. So what is my x bar over here? It's a vector. Which is that vector? It is nothing but the combination of u bar and v bar. So you choose your x. Why you will need this? You will need this to find w bar. Okay, so what will be your w bar? So this is how you find your w bar. Let me write bar over here. So this is how you find your w bar. So what x you will choose? Your x bar is nothing but it's some linear combination of v bar and u bar, such that this system can be solvable. Okay, so that's how you have to choose your x bar. Usually many times you take x bar as the average of u and v. That means you take x bar as v bar plus u bar by 2. That works most of the times. If it doesn't work, you have to write down this thing and then you first take the average and see if you can solve the system. If you can't solve the system, that means if you're not getting w bar, then you choose something else, some combination of v bar and u bar. Okay, but average works most of the times. So these are all the possibilities for a 2x2 and a 3x3 matrix. So I hope all the examples are clear. If you have any doubt, you can ask me in the comment section. And if you liked the all possible cases, do not forget to like, share and subscribe. Thank you.